Hi folks, after a short delay, welcome to the sixth lecture in this series, the one in which I make up to you, boring you about how to do scattering instrumentation yesterday. So for those who are wondering what that disappearing slide was last time, it looks like this. And I was trying to explain to you that each neutron scattering instrument is a sort of series of compromises that are made to measure over about 2 or 3 orders of magnitude at appropriate resolutions. And let's take some of those compromises, do some of those things, and not do others of them, and see how so, what are they for? Small angle scattering instruments are pretty much designed to look at length scales of the order of 10, maybe less, to a or so, maybe a little more. And it's kind of interesting region because that's they stop having properties, and they start basically being something we could identify as things. They have functions, they do stuff. So here of this diagram, you can see that I draw atoms of silicon hooked together, or bits of DNA, or a quantum corral of atoms, all very exciting. By the time I'm at the top of the small angle region here, I'm drawing pictures of protein molecules and small transistor chips. So this region is where stuff is starting to happen. And it's a very interesting region because different materials are interacting, are being put together, and they self-assemble, start doing things, they start operating essentially as machines, they start having functions. And when you ask what can you do with small angle scattering, the answer is just about anything. I know people who study complex biological molecules. I know people who study essentially material that is rotting. I know people who study chocolate. I know people who study micelles in solution. I know people who study polymers. Basically anything that has a length scale in this region where something of interest happens can be put into a SANS machine. And because neutron scattering allows a wide variety of sample environments, if you can put a window on your sample environment, you can generally do a experiment. So, angle scattering. Well, essentially, the neutrons have that right wavelength. They see nuclei, they see light atoms next to heavy ones. We're not going to talk too much about the velocity. They penetrate deeply in matter, which is why we get that flexibility in the sample environment. We won't talk elementary magnets, but very briefly, doing a statistical technique. So a statistical technique just means that when you say it's typical, it really is typical because you've measured millions of them. So how does it work? Well, here's your standard scattering diagram. You have a incoming wavelength or wave vector, an outgoing wave vector which has been deviated by 2 theta, which we'll call our scattering angle. And essentially it's that 2 theta is proportional to the wavelength of the product divided by the length that you're interested in, and inversely proportional to this, or proportional to this Q vector thing that we've defined already. And so if we take the typical wavelength of a small angle instrument, 6 angstroms, and divide it by the typical lengths we said we were interested in, we get a 2 theta or about 0.3 to 30 degrees. And this is why it's called small angle scattering, because that's smaller than the kind of angles we would be interested in normal diffractometers, which go up to basically 180 degrees backwards. Okay, another slide has betrayed us. We don't use the atomic, or nuclear, sorry, scattering lengths that give rise to the nuclear cross-section, absorption, and coherent. We basically get to use an average of the scattering lengths over a volume, a convenient collection of atoms within a structure divided by the volume of an octopi. You add up the scattering lengths, the B's here, you divide by the volume of whatever particle that is, and you'll get a scattering length density. And typically there are a few units that we're using here, 10 to the minus 6 per angstrom squared. And if you can't do the calculation, you can always go to the NIST NCR scattering length density calculator and check if the answer was right. So, what we've done here is we've taken the standard Van Hove cross-section and, okay, I'm interested in a point position by position scattering length. I'm interested in this scattering length density contrast. And I'm also going to divide by the volume of the sample. And this basically gives me something called a macroscopic cross-section. And I'm going to collect it in that are the solid angle subtended by a piece of the detector. That is simply just like the solid angle subtended by my hand as you're viewing it, hopefully through this camera. And so we're getting the differential section, and units of this are length to the minus. So you end up scattering length. You get length squared divided by volume, length cubed, you get units length to the minus 1, usually in centimeters to the minus 1. So, and that scattering strength is determined by the things we're trying to find out, namely the particle form factor, basically what shape it is, the molecules within it are arranged, and the way the molecules are hooked together, the structure factor, how the molecules or particles are separated in solution. The scattering, if there isn't too much order in the structure factor, is usually factorizable. In fact, you can take this thing, which we often call I of Q to confuse ourselves rather than this, and basically it's proportional to the number density of the particles we're interested in, their integrated scattering power, which is all this number is, the way their shape is, and the structure factor. Also, luckily enough for us, quite often we study dilute systems, so the structure factor can be just set to equal to 1. So we end up with some very simple situations. And the very simple situation number 1 that is often seen is this low Q Guinier limit. And for a discrete object, regardless of what shape it is, the macroscopic scattering cross-section near the center of one of these scattering patterns, the prefactor, basically the scattering of the particles and their scattering strength, and an exponential that's Q squared by Rg squared. And this Rg squared, well, Rg is simply the root mean square of the scattering length density contrast of the object. And that's essentially, we keep calling it the radius of gyration. And the reason we do that is because the results are exactly the same results that you get in solid body mechanics, and all of the theorems that you can apply in solid body mechanics actually apply as well. So quite often you don't have to do a complicated integral for this thing. You can look it up in a book. The Rg for a sphere is basically 3/5, well, square root of 3/5 of its squared of radius. The Rg for an ellipsoid is basically similar. Basically, if A, B, and C were the same, you'd see why we get that 3 there. And so we end up with scattering that has this prefactor, so it's nice and simple. We can go another place, to the edge of the scattering patterns. So this would be out here, and what we'll see is that we're at a high enough Q that the only thing the scattering can see is the edge of a material. The amount of edge material that you're going to see in a, which what I've withdrawn here, is going to be proportional to how the material is divided up. We find ourselves we can only see the sharp interfaces. We basically find ourselves proportional to how that material is divided up, which we already know because this is just the volume fractions of materials A and this would be B. The scattering length density contrast between the materials divided by Q to the 4. This turns out to be the same Q to the 4 you get reflectivity multiplied by this thing, which is the specific surface area per unit volume, which, if you were a colloid chemist, would be a very, you're finely dividing matter, and it nearly always is doing something at the surfaces. And SANS, or small angle scattering, is a great way of surface areas, which basically is the metric of your material or suspension. So we end up with a diagram that quite often looks like this. We call it, and there's a joke that says that all small angle scattering patterns look alike, and they do have a tendency to a certain sameness, particularly systems, but there's a lot of detail in there that you can pick out. So what we're looking at here is the form basically for a disordered system. So I'm just going to set that structure factor. So we end up with a few regions. We have the Guinier region we've already talked about, where basically if we know the volume, we get concentration out, because basically we know what the size is, we know what the scattering power is, so we'll get its number density, or vice versa. Out here in the Porod region, we can get its specific surface area, and the intensity is going to be proportional to Q to the 4. In an intermediate region, we are actually sensitive to the particle shape, and as Sonny mentioned, quite different arrangements of atoms create different fractal dimensionality, which translates into you see scattering length intensity being proportional to Q to the minus their dimensionality. So 3 for a sphere, 2 for a disk, 1 for a rod. Having said that, everything I've said so far is true for SACs. So why would you bother? Well, there's a good question about why you would bother. This is that diagram showing you how neutron scattering source intensities have changed over the last couple of decades. This is the same diagram on a log scale, put at about the same position it is rightly at for X-rays. So while neutron have been limping up from the 30s to the 2000s to essentially intensities that are equivalent to an X-ray tube, the X-ray tube has essentially gone so far it actually makes more for computers. You can't even see us intensity-wise in their rear vision mirrors. So once again the question, why small angle neutron scattering? Well, one of the answers is that brightness is never blinded by the light, you're in trouble. And it can be pointed out that neutron scattering is a fundamental probe. You never have to worry about radiation damage. And particularly when you're dealing with a new technique or a new X-ray instrument, I want you to be extremely aware that the interesting thing that you think you're finding out about your sample is not more simply described, explained by radiation damage. Your neutron scattering sample is much more likely to die of old age. The other reason is our number one trick, which is scattering length density, particularly for soft matter. Scattering lengths for X-rays, which are basically the classical radius of the gyration by the atomic number of the atom, are pretty low for most biological materials down here with low Z, but essentially they're all over the place for neutrons. The other thing about the scattering length for neutrons is that it is isotopic. We get to play games. We can get to play games where by changing the isotope we're using, we can leave the chemistry more or less unaltered, but we can dramatically change the neutron contrast we're seeing. And that trick is one that we can play here. Here are the scattering length densities of some lipids, that basically the materials that make up your cell membranes, sugar, proteins, DNA, RNA, classic biological soft molecules, sort of technological soft molecules. Here's the normal versions of those hydrogenous versions of polymers and lipids and surfactants over a range of scattering length density contrasts. And here's what happens if we replace all the hydrogen in those with deuterium. Basically, we've changed the contrast dramatically. And this enables us to essentially highlight regions or make regions disappear. If you have silica particles or say some glass wool in a vial, you basically can organize the mixture of H2O and D2O so that the glass wool disappears and you can see a feature that was otherwise hidden behind it. Now that's an optical analogy, and it's a kind of trick played with by fiddling around with the refractive index of a glycerol water mixture, but we can do exactly the same thing. So if we were like this, we couldn't see any and scatters light as a mess. Now the scattering we see is the scattering from those two Pyrex spheres that are hidden behind all that glass wall. Same thing happens with neutron scattering. Okay, the other reason that we care about this part of the talk could actually be called How Neutron Scattering Changed the World You Live In. We go back to the 40s, and Dubai had done some absolutely wonderful work with X-ray scattering and small angle light scattering on the dilute polymer in a solvent. And he discovered a Guinier region, and a region where it looked like a thin rod, and a region where it looked like a random walk, so Q to the -2. And he described the scattering in terms of the famous Dubai function. And this was all done by the late 40s, and this is basically, so now you know polystyrene in dilution, which is wonderful. Good for his Nobel Prize, thank you very much. But technologically, you've got to ask yourself, who cares? Nobody cares soup of polymer in a melt, or at least polymer in solution. What they care about is a piece of plastic that you can wrap around a cell phone. And to study a piece of plastic, or the microstructure of a piece of plastic, you have to see the correlations between the atoms and see the correlations between the same atoms or the same polymer chain. And if you look at this diagram I've drawn here, the interchain correlations, sorry, the intra-chain correlations between this molecule that you can tell is different from the others only because I've drawn the line thicker, is going to give scattering in the same position as this correlation between that molecule and another molecule that it has nothing to do with. So the scattering contrast or strengths cannot be angled. We play our game, and Flory gets a Nobel Prize. Why? In 1974, prize because he gets to see that is in a concentrated solution of polymers in polymer that the gain is basically cannot tell itself from anybody else. There is no excluded volume. It acts like it's in an ideal solvent, just as it would have if it was in a dilute ideal solvent, and Dubai had been looking at it. And there was a lot of indirect evidence for this. Flory was a very bright guy, but there was no direct evidence. And the reason he probably got the Nobel Prize in 1974 rather than a few years later was because at about the same time, or about a year or so before he got this, people started doing exactly what I suggested a few minutes ago. What they did was they took deuterated polymers, because they now knew how to replace all the hydrogen in a polystyrene chain with deuterium, and they added a few hydrogenous molecules. And they had a system in which the contrast between different parts of the same molecule was wildly different from different parts of different molecules. So you can now actually see the scattering from this molecule independent of the scattering from everybody else. So you know what its shape is, you know how it's interacting with itself and everybody else. And after a few years, they even realized, what? The point is, the answer to this is that they even worked out after a while that they didn't need to go dilute solutions. They could just basically mix deuterated polystyrene and hydrogenous polystyrene together, and it would be the contrast of me versus the average of everybody else. And they discovered that this Gaussian chain behavior, this Q to the -2 behavior, was very, very accurate, but actually slightly wrong, which is why a few years later, De Gennes got a Nobel Prize, but we won't go into that right now. Okay, so why did it change the world? Well, it changed the world because for a while, before Flory got his Nobel Prize, people would ask about what is the amorphous phase, what is the nature of the amorphous phase in the polymer melt, this technologically important thing. And there were a number of competing models that fitted the scattering, which didn't tell anybody. And essentially, by doing one experiment, or 3 experiments as it turned out, 3 different groups showed that this was the model to think about. And what it meant from then on was that the world could just test predictions made by theoreticians, and it could move on. So, if you took your molecule in a polymer melt and the scattering from it, and you wondered, what happens if I stretch that polymer melt? What happens to this molecule? How does it behave? The answer is you could measure that scattering because of that contrast. And because I stretch this molecule in this direction, because we're looking, scattering is in reciprocal space, the effective scattering strength shrinks perpendicular to that and extends in the direction that I have shrunk the molecule. If you ask yourself, what happened if I put that polymer into a thin film that was actually thinner than the radius of gyration, what would happen to that polymer? You could work out a way of doing an experiment like that. Basically, you take a stack of thin films and you put them into a sands machine. If you were worried about what happened if I tied 2 immiscible polymers together, what kind of structure do they organize into, you could study diblock copolymer phases. crankbaits did in the 90s. If you were worried about how molecules exchanged in suspensions of micelles, what you could do is build a whole bunch of hydrogenous micelles, or deuterated micelles, and then hydrogenous micelles, and you could throw them together in solution, and then you could do scattering that basically would see that as time went on, the micelles would mix. Molecules from this micelle would leave, transfer through the solution, and wind up in another micelle. And you could watch the scattering from the contrast as it went to the average contrast decay over a day. So you would be watching structure and kinematics of materials. All of them, in every case here, that are important technologically, and you can't really get this sort of information any other way. So I'm going to bring myself into the story here. So a few years ago, I decided to do a little bit of, or decided to a little biological engineering with lipids. And basically a lipid is the oily salt that makes up most of your cell membrane. And we worked with two lipids, and one was a thing called DMPC, which is a 14-chain lipid. So this is its head group, and it's got a long double tail of essentially an oily tail that dislikes water. So if you put it in water, this forms bilayers. Basically, the water, the oil would rather be stuck with other oil. The amount of tail material you've got is such that it is thermodynamically satisfactory for this molecule to organize itself into layers. And you mix it with another lipid called DHPC, which is a short-chain lipid, which you can see has a very big ionic group compared with other small, shorter carbon chain. It actually starts to form nearly spherical micelles because it hasn't got nearly as much oil to put in. So basically its surface area to volume ratio is rather greater. However, when you put them both into solution together, you get these things called bicelles. And they're called bicelles because they're layer. This is what the technical name for this membrane is. And micelle, so we get bicelle. So basically what happens is this is a little object where it forms a rim around a bicycle wheel body formed by the bilayers. And if you read the books, at least initially, you will find that bicelles, the disk size is controlled by the amount of short rim material you put in solution relative to the long disk body molar ratio. And these things are called ideal bicell models. There are a couple of them depending on how you exactly calculate how much material is needed for a rim and how much is needed for a body, but they both basically predict that the size of the bicell is controlled by the lipid molar ratio. It doesn't absorb the neutrons because we don't put very much in. It takes a while. You basically need millimeters of hydrogen to all the neutrons, and effectively in one of these solutions we're only going to put in a few hundredths of a millimeter of hydrogen. So, whoops, getting ahead of myself. So why do I care? Why do we care, rather? Because we thought we would use these things to move around transmembrane proteins, which are encoded by 40% of your genomic, and are designed to sit around in the layers of your cells. That's what they do, that's where they have functions. And what we thought was that using these bicelles, which are similar to your body's cell walls, to create a great little delivery system for one of these proteins that might be used in therapies. And we thought we would be measuring bicelles and with transmembrane protein and essentially technology that way. But we actually, when we started looking at this, we actually found that there already was a technology. The answer to Fan's question is that the bicelles essentially want to be in solution. If I'm into another lipid, I'm going to want to hang on to the oil. So once they start to form, they will continue to form. There are, and you're making me get ahead of myself, there are some micelles probably still in solution. But basically, once the oil gets together, it finds that being in contact with oil is much more fun than being in contact with water. So it's hydrophilic, hydrophobic interactions all the way. Yeah, I know, he said he understood that part. Thank you. Okay, so already there's a bicell technology, and if you go to the Avanti website, they will tell you that you can use the bicell model, and you can buy DHPC and DMPC from them, and you can mix it up, and they'll give you a recipe for doing it. And the reason you're going to mix it up is because if you create some of these micelles, let's say these bicelles, and you put them in a magnetic field with some proteins, you can align those proteins, and this dramatically increases the accuracy of an NMR determination of protein structure. Don't anybody ask me about this. This is a technology. It already exists. It's magic as far as I'm concerned. I'm not an NMR expert, but you can look it up. Okay, so we asked ourselves the question, do we actually know this? And the answer is, well, had anybody actually known this? Yes, it improves the accuracy of NMR results. And yes, the things were probably disk-like, but did anybody really know that this whole idea of rim material, body material was true? So we thought we'd do a few experiments. The first thing we did was we tested the IBM, which, as you may remember, said that the only thing that matters about the size of one of these things is how much rim material I put in solution as a ratio of how much body material. And for this, we did the simplest thing you can do with small angle scattering. We did a Guinier experiment. All we did was we kept the the molar ratio of DMPC to DHPC at about a factor of 2, which basically gives a volume ratio of more like 4 or so, 5. But basically the same ratio of molecular species. And we studied hydrogenous bicelles, that is not very many of them, so they're not going to eat all the neutrons. And we put them in a solution of D2O. And the only thing we did was change the total amount of lipid we put in there. And the ideal bicell model would say that if we did a, oops, forgot to fix this slide. If we did this experiment, the RG for every one of those things, as we changed the concentration, would be the same. And so if we did what we can laughingly call a Guinier fit, because essentially what you do with Guinier is you plot the log of the scattering length intensity versus Q squared, and you just draw a ruler through it and you get the gradient. They would all have the same gradient because this would be negative RG squared Q squared on 3. And what you can tell from these 3 different gradients is that we have 3 different sizes. So the ideal bicell model is instantly in trouble. So the answer to this question is, never mind the fact that there's a technology that works, maybe they aren't actually disks. So here we can do the scattering, and we have to go a little bit further out in the scattering pattern. And basically, instead of staying in the Guinier region up here near Q equals 0, we go out a little further. And we do a relatively complicated Rayleigh-Gans fit, which is the name of that integral of the scattering length density. And we rotationally average the scattering pattern. And what we get, as we change the concentration, and assuming this disk-like model, is a pretty good set of fits that indicate that they are disks. And they're pretty much as simple as the one drawn in my cartoons here. So the next question we have to ask is, so maybe the lipids aren't segregated. Maybe they're disk-like, but there's a lot of intra-bicell motion, so there's a lot of mixing within the bicell. Actually, if this view graph does not answer your question, I'll be surprised. Okay, so maybe the lipids aren't segregated. So what we did here was, instead of just doing what we've been doing already, was just taking purely hydrogenous material and putting it into D2O. What we did, we stayed with a hydrogenous rim, and we put in deuterated DMPC, which costs a lot, but doesn't scatter very much relative to the D2O. And we get two scattering patterns. This is a scattering pattern we got before, which is basically just this disk scattering pattern. And this is the scattering pattern, which is now the scattering pattern of essentially no contrast between the body of the material and the D2O. And essentially all the scattering is from correlations around the rim. And so what we see is essentially the scattering from this relative to that. And essentially when you do that, you get a fit, which is essentially telling you the diameter of that rim. And the answer to Fan's question is that after you've done this fit, these bicell rims turned out to be about 94 nanometers across and with a polydispersity of about 10%. So they were ridiculously segregated and very, very uniform. So we'd asked a series of questions with small angle scattering, and we got a series of answers. We'd done Guinier, which we could have done. We'd done a disk form factor fit, which we could have. At that point, Sachs would have run out on us. Because we can do hydrogen deuterium contrast, we can basically answer this rim question. Okay, now if anybody's got a question about bicelles that goes a little bit further, you'll have to kind of wait for an outcoming paper. Basically the answer is thermodynamics. The CMC and the bulk solutions of the different materials is different. Basically the rim actually doesn't mind sitting around in a spherical micelle, so some of it is still out there in solution. So there's less rim material than you think there should be, so the bicelles wind up being a little bit bigger as you change the concentration. Okay, how do we measure this? Well, we come back to those pictures I showed you last time of SANS machines. When you strip out all the verbiage and shielding and stuff, they're actually pretty simple objects. They're pinhole cameras. Very long pinhole cameras, but pinhole cameras nevertheless. And you can probably see this a little bit better if I take those diagrams that I showed you last time of a continuous source instrument with a velocity selector and a detector, and I'll put a sample in on this one, a pulse source instrument where we're going to use time of flight to measure the neutron wavelength, and a detector to measure the scattering length. And what I'll do is I'll put some pinholes on that, and what I can get if I did that is I would get the image of the direct beam, because there would be very little scattering. And the object is the entrance aperture, and it is blurred by sample scattering. What does that mean? Well, there's no sample here, so all I get is a small dot that is essentially the image of this entrance aperture using pinhole ray optics on the detector plane. If I put a sample in, the image that I originally got is blurred by the fact that I put this sample in here. And that small angle scattering is essentially what I'm trying to get. In more formal terms, you have to put in the pinhole optics of the thing, but what is happening is the detector pattern is the direct beam image convoluted with the scattering pattern, or the scattering function. So what does it look like? Well, another picture pretty much like the ones I already showed you. We look at a cold solvent, trying to look at large-scale structures, set our length scales. We have a velocity selector, basically one of those fans which chooses a narrow outskirts of Sydney in Australia, and I helped build it about 5 years ago. And then after the long tank through which we can move a 1 meter by 1 meter detector with about 5 millimeter resolution, and using the scattering pattern on that and the scattering vectors we measure as to where the neutrons turn up on the detector versus the wavelength, we can get a scattering pattern which we can turn into a small angle neutron scattering measurement. And here again is EQ SANS, which I mentioned last time, which is the extended QRH SANS here at SNS. Essentially, it's the same deal, except that this, I look at a high moderator, which is of the SNS's mercury target, which gets hit 60 times a second by a proton beam, sends hot neutrons into this, which are very cooled down by hydrogen, and flash out along this instrument, which is 5 meters long. I measure how long they took to get there, for how long they had to travel, and I get their wavelength. I measure how far off the center they are on a detector. I get their angle. I have to do a little bit of chopping of the system to make sure I don't get frame overlap that we talked about briefly last time. The sample position is 14 meters from the moderator, and the detector can be moved from about 1 meter from the sample to about 10 meters. And so, this comes to a bunch of practical considerations. And basically, these are the practical considerations which I'm not going to ask anybody to memorize. But you've got to ask yourself two things. Q range, which is basically saying what size ranges am I interested in. And I might have to set the instrument up more than one time. There's a limit how far I can go in one scattering setting. And resolution, which is basically how accurate the measurement I'm doing is. Delta Q on Q, which is basically translates directly through quadrature in terms of the accuracy of the angle I'm measuring, because there's always a range of angles that we let into the machine, otherwise we wouldn't see any intensity. And there's always a range, an accuracy to which I can measure the angles. As long as he doesn't fall over, we'll be fine. We've got a sleeping member of the audience here. I hope none of you are sleeping. And that accuracy translates directly into the accuracy you get in lengths. And that's important because that accuracy can smear the way a scattering pattern looks. It'll shift peaks that are on shoulders. And even more importantly, if you have things that have a range of sizes like our bicelles, you have to take into account that they all look slightly different in size because I had a range of wavelengths that I was dealing with. So I'll have to take that resolution factor out. And basically, how do these things factor in? The choice of wavelength basically gives you, from the size of your detector and the maximum angle you can see, it gives you a maximum Q, and through the minimum wavelength you're looking at, it gives you a minimum length that you're sensitive to at a particular scan. The size of your beam, basically, your direct beam without anything, is essentially going to be the limit on your the smallest Q you can see at a particular setting, because you won't be able to see any scattering in here because you don't want to have too much scattering in here. Otherwise you'll have multiple scattering and you won't be able to untangle which scattering did which. So basically, and also this is too intense for your detector usually. So basically you end up covering this with a beam stop. So basically the minimum Q you can see is basically the size of your beam stop divided by the sample to detector distance L2 divided by the maximum wavelength you're looking at. And of course for a velocity selector on a continuous source they're the same number. For a pulse source they're different numbers. You'll be taking a range of scattering lengths here. Sorry, range of wavelengths. And that gives you a D max. Angular resolution, you basically can do the math on this, and it's just pinhole math. It turns out that if you want a particular delta theta, angular measurement, angular accuracy of your angular measurement for a given L1 and L2, entrance to sample distance and sample to detector distance, your highest intensity is when you're in the focusing condition, which is basically just means that from your detector, the sample aperture and the source aperture look the same size. And it turns out the beam image in this situation is conical, which I've tried to draw here, and that's basically the radius that your beam stop, the full width of that is the radius of your beam stop. And the best intensity, which is why happens for when the two pinhole lengths are the same, L1 equals L2, and that's the reason that we have those guides to basically transport this entrance aperture closer to the sample as we move the detector in to measure over different Q ranges. So, how do you do a measurement? Horrifyingly enough, one measurement isn't one measurement. It's basically 5. The first measurement is basically you just open up the pinhole of your sample aperture, and using a calibrated attenuator, you dump it on your direct beam. And it gives you the thing called the direct beam flux, which is the neutrons per seconds, neutrons per monitor. But what it's really giving you is the aperture area. Remember, scattering length, the macroscopic scattering length is an area per unit volume. And this is that area. Basically, it's the area of your entrance aperture. So the full intensity of the direct beam actually really represents, quote unquote, the full area of your entrance aperture. The next thing I'm a little bit interested in is the transmission of my cell, because basically even if I scatter in here, if I can't scatter out, if the neutrons can't leave or get through the material, I need to know what the transmission is. So I put the cell on without a sample. There's supposed to be nothing in here. Unfortunately, it's been shown with something. I basically need to know the transmission of the cell. In most empty cell transmissions for cells, they're usually little glass cuvettes with 1/10 of a millimeter walls, and they usually have little flat bodies. And they're about a millimeter thick here, with 1/10 of a millimeter walls or less, and it's usually about 95%. I also need to know the transmission when I put in the sample. And so I put the sample in front of the aperture and I measure the direct beam transmission, and from that I get the transmission of the sample, the transmission of the empty cell, and the area that my direct beam intensity represents. Okay, now we come to doing some scattering. We need the empty cell scattering because we're not interested in how the walls of my empty cell scatter. So without any sample in here, I measure the scattering, and it should be very, very weak, because that's why you made your cell out of something that didn't scatter neutrons very well, or certainly not over the scale range that you're interested in for your sample. And you get a complicated mess, which turns out to be the incident intensity, the transmission of the cell, the scattering macroscopic cross-section of the cell, and the solid angle of the detector element, because we're all talking about a particular pixel and a particular wavelength and scattering length. Then finally I do my scattering pattern. Finally, you were asking. And I get the same things, only the transmission of the source plus the cell and a scattering. and basically I get its macroscopic cross-section. If you came up here, you do the math, you'll find that the same term that I measured up here can be put into this equation, and the thing that I'm actually interested in, this macroscopic cross-section, can just be taken as the intensity of the scattering that I see divided by its transmission, the intensity of the cell scattering divided by its transmission, take out the incident intensity, the solid angle subtended by the detector element, the thickness of the sample, and the reason only the thickness appears here is because that intensity actually already includes the area of the sample. So why isn't this d sigma d omega, the cross-section divided by the volume? The volume of the sample is the area divided by the thickness. And the area is already in here, so it's gone. Finally, I've now got a whole bunch of intensities at a various bunch of Qs with resolutions, and if I'm on a pulse source, I'm going to end up with a pattern that looks like this. If I'm on a spallation source, at every time, for every wavelength at every time, I'll have a pattern that looks like this. So here we are on Quokka, some of the very first data taken by Elliot Gilbert after we finished building the instrument, and he kept this sample. It's paraffin that he'd aged for 10 years because he was interested in how soft matter kinematics changed over a 10-year period. And we measured over 3 scales. We did a 45-minute run at the 20-meter setting of the instrument, a 10-minute run at the 2-meter setting of the instrument, and then we did annular averages of all those data sets to get this pattern. And the thing to notice here is that this pattern is taken with the instrument at its maximum length. This pattern, all of this pattern, is actually more or less within the beam stop area of this pattern, which was taken 10 times closer to the sample. On EQ, some of the first work they did was on dendrimers. On an EQ sands, they didn't move the detector around in this case. What they did was, because they can change the wavelength frame they're looking at using those frame overlap choppers, because they have a much broader wavelength frame, because not only do they have the wavelength frame from the ratio of the beam stop size to the edge of the detector, they also have this multiplication by the range of lambda min to lambda max they can use. They can actually find it's rather more convenient to just change the time of flight chopper range and cover a similar range in 2 steps to what we covered in 3 steps on Quokka. And so that's putting it all together. And then someday you'll analyze this data. Okay, I made a big fuss about absolute normalization, and nobody asked me this question. I've been asked this question a couple of times. You say to people, oh, fractal dimensionality, very wonderful thing. The fractal dimension of a disk is 2, so the scattering is going to be Q to the minus 2. And a little while later you tell them this, oh, Gaussian chain. If you look at this over this square range, it's a random walk. The scattering's Q to the minus 2. And then you show people the scattering from a thing, you tell them is a bunch of disks, and then they look at the scattering. And nobody ever bothers to look at the scattering from these disks and realize that Q to the minus 2 didn't actually turn up. And the reason it didn't turn up is that these bicelles that we measured are actually a little bit more like lozenges, and you'll find quite often that fractal dimensionality is a little bit less telling than you'd think. These disks are a little bit like little clumps, like pills. They're not quite big like quarters. You'll find quite often that membranes aren't like flat sheets. They tilt up, so you're not looking at Q to the minus 2, you're looking at Q to the minus 2.5. So then, if it had been the Debye function, if we'd seen, why would we have said that somehow the bicelles weren't forming some kind of weird chain-like structure which would align perfectly well in a magnetic field and give the of that gives us better NMR resolution? And the answer is absolute normalization, which is disgustingly easy to do with SANS if you follow that prescription. And that prescription, you should understand it, but you probably don't have to memorize it because it's built into how most of the scattering experiments your instrument responsibles will let you do. And what absolute normalization forces on you is that you have to decide between competing models. You know how much material you put in, you know how much scattering power that will be in that model, and you know how much scattering strength is in there. So we know that the bicelles are forming little chunks. They're not forming big goofy tubes because there's simply not enough scattering strengths for the tubes. There's not enough material to make that. And incoherent scattering, which is the bane of our existence, which is the scattering that doesn't have anything to do with structure, which Sonny mentioned, actually, for neutron scattering experiments, masks what's going on at basically a lower Q than we like. But it can always be used to double check whether your absolute intensity is correct, because things that are essentially hydrogenous, say fully hydrogenous water, will give you an incoherent cross-section of about 1 centimeter to -1. Fully deuterated solutions will give you about 1/20th of that. You can see this is done with 1/20th with a fully deuterated solution of bicelles. So you can always double check your absolute normalization, which gives you a good idea whether your scattering power and number density is right for your model. Okay, I've dissed neutrons. I've upped neutrons and I've dissed X-rays a bit. X-rays are enormously useful, and I think there's going to be a biological scattering talk a little bit later given by Jeremy Smith, which will probably point out that X-rays can give you an enormous amount of information about structure, and particularly in correlation with neutrons. And it is always, because you should always know as much about your sample as possible. Well, it's quite often useful, particularly with a dilute solution, to have an X-ray measurement. But one thing I'd like to point out, and this is sort of an emerging technique, is that parallel measurements between SANS and SACs have the potential to be incredibly powerful. And this is, but you don't need an APS for this. All you need is a SACs machine that's a typical rotating anode. And this one happens to be in the guide hall, opposite the guide hall at ANSTO. And if this picture had been taken a little bit later out this window, you would have seen the tube of that Quokka SANS machine. But if you put in the math, essentially the scattering you see for SANS, the form factor is the SANS form factor. For SACs, you have the same number density, but you have a different form factor. Both of them have the same structure factor. They both have backgrounds of this sorts, but you can chop them off. So if you put them together, and you can deuterate the solutions if you like, X-rays don't care, you get the same particle number density, same structure factor, but you get different internal particle contrast. So the structure factor will cancel out. So if the structure factor was going to be problematic, if for a concentrated solution, you're going to get scattering at the same sort of Q range for the internal particle structures you are interested in, essentially, you don't care anymore. This ratio only cares about this ratio to this ratio. So if you get parallel fitting of these two scattering patterns, you can get structural information internally just the way that SANS got it for Flory all those years ago in systems that really do matter. And systems that really do matter these days are biological systems in physiological conditions. And what there's a lot of interest in the moment is crowded biological systems. People now want to know, okay, we've got all these wonderful pictures of the structures of proteins in solution, but basically proteins aren't really too much in solution when they're actually doing something in the body. They're in a cell wall. They're mixed up with something else. If they're in a cell wall, how can you make that structure, while they're actually doing something, stand out. And this is a way, hopefully, to do it. And one that I intend to pursue over the next few years with collaborators who are in the room. So I hope they're listening. Okay. Emerging techniques too. Don't try to understand these, but they are available. Because electrons have a refractive index, you can actually make lenses for them. The lenses are terrible by the standards we are associated with optics. And also, unlike optical lenses, they turn out to be concave lenses because the refractive index for neutrons is negative. However, if you put, I think, 6 of these together at NIST, and these things essentially are like Coke bottle bottoms, and have a radius, I think, of curvature of about 1 inch, 25 millimeters for you SI types. If you put 6 of them together at the sample position at NIST, or 28 of them together at the sample position at NIST, what one can do is one can focus the entrance aperture onto the detector position at the maximum distance of 15 meters here, 15 meters there. And what one ends up with, and what this means is that even if I increase the sample size, I won't increase the absolute radius of the beam image. I'll screw up its shape a little, but basically I can get a lot more intensity for giving up a bit of resolution without having to increase the size of my beam stop. But you have gained intensity, the resolution you get in a standard pinhole setup. But that's okay, because in a standard pinhole setup, if you do the math for 15 meters here, 15 meters here, these pinholes are so small that you wouldn't get very many neutrons through them, and you'd probably see nothing but background by the time you got to the detector. And this turns out to be some data we took on Quokka when we started up a similar pinhole system at 20 meters. And what we're looking at here is the packing between in silica spheres and an OPAL chip. And we're actually looking at the crystallography of these spheres. So they're hexagonally close packed and about 4,000 angstroms across. Okay, USANs. One of these is available at NIST, and Oak Ridge still has bragging rights because Misha Agamalian in the 90s was the man who made this technique, which had been moribund, existed for about 10, 15, 20 years, but was kind of moribund for technical reasons, SING. What you do here is Bragg scattering from perfect crystals, essentially a pair of them. We actually multiply bounce off them. And Bragg scattering from these perfect crystals is very, very narrow. So if this one's in the Bragg condition and at the same orientation to this one, neutrons will get to the detector. If I put a sample in here, I will get very slight angles of deviation, which will mean that some of that scattering will disappear from the Bragg condition. But if I tilt this second crystal slightly, it will get to the detector here. And what I'll see is a broadening of that Bragg peak, which can be turned into measurements of the very small angle scattering. And that small angle scattering gets you down to a Q-min of about 10 to the minus 5 inverse angstroms, which, if you work it out in distances, turns out to be about 60 microns, which is about half the width of a human hair, which is about a 20th of a millimeter. So these things are almost big enough to see, but some of them are invisible for obvious reasons because they don't have good optical contrast. Another technique which is emerging, and I'm actually working on at the moment, but it's been developed at a reactor in Holland in Delft, is called spin echo sands, and it uses that neutron spin optics that I talked about before to use the fact that if you tilt magnetic fields in a way that Dieter Richter in a couple of talks from now will not, you can actually demonstrate that neutron spins are birefringent. So you have matched and opposing fields that actually have tilted boundaries, and this is done in a cute sort of technical way. You actually have birefringent neutrons. They actually separate, and this is the distance. Remember, SANS is always the correlation perpendicular to the direction the neutron is traveling. Q is this direction, so it's this 2 pi on this d. You put them back together, and the fact that they've traveled different distances through the sample gives them a phase difference, which spins their neutron polarization. If you analyze this, you can actually measure a precession, a tilt in the magnetic moment, which gives you a very small angle scattering transform. It's not quite the Q transform you're used to. It turns out to be the Q space transform has an effective Q min of about 10 to the minus 5 angstroms to minus 1 again. That turns out to be that same sort of half the radius of your human hair limit, and to about an order of magnitude below that. But the great thing about this is you can do them on concentrated systems. And one of the most amazing things I've seen done with this is they've done measurements on yogurt, they've done measurements on cheese, they've done measurements on milk, they've done measurements on all sorts of goop that actually matters, that can simply not be measured any other way. Their main problem at the moment is that it's so unlikely that anybody will get direct information on concentrated systems like this, that the theory is totally lacking. Everybody's loves to tell you about things floating around in dilute systems which have no real technological interest, but if you ask them what's happening in a concentrated system, they have only a few vague answers like, it will probably get scrunched up. And for those who are interested in Liouville's catch again, these turn out to both be 1D techniques. I'm only looking at the correlations in one dimension, that is perpendicular to this direction. I can't see correlations out of the plane for this Bragg scattering or out of this plane for this Surges scattering. So hopefully I've convinced you that while neutron scattering is a little slow, the fact that neutron scattering contrast is nuclear and not chemical gives you enormous strengths. Isotopic substitution means you can highlight subregions against a background of similar length, similar stoichiometry, and you can see things that are just otherwise invisible. And the classic example is that polymer chain in a polymer melt, but the same trick gets played over and over and over again, and the limits to that trick are only the limits to what you can deuterate. And the beams are gentle. You can measure the same thing over and over again. You can do absolute normalization. You can take a sample from your PhD thesis, and provided you have made sure that it has not rotted, 10 years later you can find out to your disappointment that the absolute normalization of it has not changed a whit since you wrote up, so there's not another paper in it. Sorry, Elliot. And particularly, and of increasing interest, we don't damage biosystems. And you can measure them under near physiological conditions. So no special sample environment is required. So whatever you can put into it works. And I've seen things that are basically little cells are rotting. I've seen people doing scattering over quote-unquote shear cells that are the same things that measure the viscosity of dough. And literally they're little propeller wheels in little aluminium cans, and you just come into the side of those little propeller wheels and you measure the sand scattering. And you can measure just about any sort of sample which has a length scale of the order of a few angstroms to a few thousand angstroms. Or if you go to those last techniques, I measured a few tens of thousands of angstroms. And you can get information that you can't get in any other way. And I'll stop preaching to you now and accept any final questions. And I'd like to acknowledge all the people, once again, who I stole from. And it's a larger and different list this time. And I'd also like to plug a few of these reference things. Some of you are obviously already aware of this, but over the last few years, Bulam Hamuda of the NIST Center for Neutron Research has put together a very compendious list of everything NIST knows about neutron scattering, and it's full of reasons for why nearly everything at NIST is done. And it's well worth a read. And thanks for your attention, and if you have been paying attention, the reviewers of your proposals and papers, and they may include me, will also possibly one day thank you. Thank you. Any questions? I hammered into a submission. Multiple attendees typing. The shortest time scale I can perform with sands. It's an interesting question. On a spallation source, people keep thinking about doing it in a flash. You can perform, if you can repeat the measurement, you can go quite fast. There are techniques on a spallation source, if you could doing it, like say I was hammering a solution with pressure, or I was pumping it with a pulse. You could do scattering, which was correlated. There's a technique called Tisane where you take a continuous source and you actually put a chopper on it, and you get to play a kind of little frame overlap game. And those techniques with intensity can get you down to about a millisecond. They're a little bit specialized, but they exist. If you have a specific system you want to measure, and you can find out my email from, well, Mayon or later, and I'll answer your question on that. Generally, SANS experiments take minutes. You might have, your integrated time might have to be minutes, but if you can split it up into tiny little chunks of reaction time, you can do fast experiments. People have done diffraction experiments on things that are essentially burning. It's probably possible with SANS, but I don't know how fast those have been done. And exploding, I think, at Lance. Thank you, LSU. Any more questions before we quit? It's like in a seance where they say, "Spirit, are you with us?" Is the spirit going to say no? Okay, kids. Thank you, everybody. Bye-bye. Anybody who's still there?